Good day everyone. Today I will be discussing how to determine the natural frequency of free vibration of single degree of freedom systems as part of the course Me22088. My name is Dr. C. Sendamarekana and I am an associate professor in the Department of Mechanical Engineering at SVC. In this session, we will explore how to determine the natural frequency of the given systems. We know that natural frequency is very important. As you also know, the system at which system tends to oscillate with a small disturbance is called natural frequency. This is a very critical parameter in many engineering applications. If we determine, then it is very easiest for us to avoid resonance in bridges or otherwise in buildings or in machine elements. Also, it is used to design musical instruments, and also we can understand the machinery vibrations.
Dear students, now we are going to see how to determine natural frequency of this cantilever beam. This cantilever beam length is L and it is having a weight at its tip. At the tip of the cantilever beam, we have loaded the mass. The mass is going to be M. Because of this mass, cantilever beam is deflected for a length of X. So under this condition, we are going to determine the natural frequency of the system. For this, we already know that in the strength of materials, the stiffness of this beam, cantilever beam, is given as K equal to, that is stiffness equal to 3 times of Young's modulus I divided by L cube, where E is Young's modulus, I is moment of inertia. Otherwise, we can also call it as EI, flexural rigidity of the beam. If the flexural rigidity is more, then the deflection is very less. We also know that in our previous classes, the harmonic motion equation can be written as mx double dot plus kx equal to 0. Using Newton's method, Rayleigh's method, we determine what is the natural frequency for this equation, that is natural frequency omega n equal to root of k by m. Equation 1 can also be written as x double dot plus k divided by m, x equal to 0. So otherwise x double dot plus omega square x equal to 0. So from equation 2 and 1, we can able to see that omega square is equal to k by m. Omega square equal to k by m, that is come as omega equal to root of k by m. So in this way, we are using the formula natural frequency equal to root of k by m. Now, you take the equation 1, substitute k equal to 3ei by L cube. It will become as mx double dot plus 3ei by L cube x equal to 0. Otherwise, simply we can put omega n equal to root of k by m, is it not? So, root of 3ei divided by L cube and mass will come into picture. So, for this given beam, natural frequency is root of 3ei divided by ml cube. This can be written once again. The denominator is ml cube. As discussed in our previous problem number 1, we have to know the deflection equation for this kinds of beams. The deflection for fixed beam. This you can know that it is a fixed beam. You can see that the load is now positioned exactly at the center. We can take it as P. At center means L by 2. The total length of the beam is L. So now it is very important. We should know what is the deflection equation. The deflection equation is PL cube divided by 192 EI. So in this case, what is the stiffness formula? Stiffness K equal to load divided by deflection. So if we substitute this, we will get that stiffness equal to 192 EI divided by L cube. Now let me take the same harmonic equation mx double dot plus kx equal to 0. That means x double dot plus k divided by mx equal to 0. What is this? K by m omega n square, that is the natural frequency, equal to k by m. Once again, we can rewrite natural frequency as root of k by m. Okay, we have to keep this always in mind. So when I substitute the stiffness value for this beam in this equation 1, that is natural frequency equal to root of what is k? 192 EI by ml cube. Here m is to be substituted from the natural frequency. So in this case, this is the natural frequency formula for the fixed beam when the load is centrally placed. What is the unit for omega n? Is radians per second. We can convert natural frequency omega n, that is radians per second, to hertz. That is, the formula is F1 equal to omega by 2 pi. So omega is already root of 192 EI divided by ml cube into 1 divided by 2 pi. So that the natural frequency in terms of hertz we can able to calculate by using this formula. Otherwise, we are converting the radians per second to hertz. We are going to see problem number 3. Here in this problem, we are having a simple U-tube manometer. This is filled with liquid as shown in the figure. We have to determine the natural frequency of resulting oscillating motion if the minimum length of the manometer tube is 0.15 meter. The oscillation is there means then the displacement is in terms of x. So let me determine natural frequency for this given manometer tube. M is, it will take mass M, that is going to be the mass. The rho is nothing but the mass density of liquid. Then cross-sectional area of the tube is A. I am once again stating that A is nothing but cross-sectional area of the tube. Now, what is the mass of the liquid column? Mass of the liquid column is nothing but density into area. When we say x is displacement, then dx by dt is, we can written it as x dot it means velocity. So in all our derivations, if x dot means it is velocity, x double dot means it is acceleration. That means x double dot means d square x by dt square. Now we go into this problem. We are going to solve this using the energy method. In the energy method, total energy of the system is constant. That means kinetic energy plus potential energy equal to constant. What is kinetic energy of this moving liquid? The kinetic energy of the moving liquid, very simply we can substitute of mv square. Here of mass is, we can see that this is mass rho a, and here it is going to be with respect to the liquid column, so it is rho al into velocity we are putting in terms of x dot. Since it is velocity square, so x dot square. Potential energy is going to be written in the form of rho a g. Okay, that is potential energy formula is simply, I'm writing it here, mgh. So mass we have to substitute. Okay, then g is the gravity and h is the, for different types of problem it is height. Here it is going to be the liquid column. So it is going to be rho agx, okay, into x. So this is nothing but the mass. How this mass is calculated? Rho a into the displaced liquid column. So for this potential energy, we have to substitute x. In the previously, you can see that we substitute in this formula mass equal to rho am. That is the total length of the liquid column. Here in potential energy, we are substituting only x, that is the displaced liquid column. So this is m rho a g. G is to be gravity, m into g. This one is, this part is once again the displaced liquid, h, the height of difference. Okay, so now you can understood very well. So the potential energy is rho a g x square. Now we substitute this. Okay, in this total energy of the system is constant, is it not? So in that we are going to substitute. Then at the case it is of rho a l x dot square plus rho a g x square equal to c. We have to differentiate this with respect to time in order to get the natural frequency. When we are differentiating this with respect to time of rho al x square, it will become as velocity. If it's differentiated with respect to time, it will become as acceleration x double dot. This 2 will come here. So this two will get cancelled. So rho al x double dot plus rho ag 2x. Once again, we will get the x dot. Here also we will have that x dot will be there. That is, when I differentiating x dot square, what is the meaning means 2x dot. Once again, it is to be differentiated means it will become as x double dot. X double dot means you know that acceleration. Similarly, in this case, x square differentiated means it is 2x. Then x has to be differentiated with respect to time, that is x dot. Okay. So now, commonly, we will have x dot that will get cancelled. This is, since the constant is differentiated, we will get 0. Now, if we rewrite this equation, what will happen? Rho will get cancelled. A will get cancelled. At last, we will have L x double dot 2g. So L x double dot plus 2g equal to 0. Okay, sorry, x is there. 2gx is equal to 0. So in this case, you once again rewrite x double dot plus 2g by l x equal to 0. We know that from the previous two problems, this thing is nothing but your natural frequency. Okay, this thing is nothing but omega n square. So what is the solution? Solution is omega n square equal to 2g by L. Okay, otherwise omega n equal to root of 2g by L. So with this, we can able to determine the natural frequency for this problem. Okay, um, since in order to understand, just I want to solve this. What is this given problem here? It is going to be 0.15 here. This is to be substituted in this. So see that I am substituting here omega n equal to root of 2g by L is 0.15, where g is 9.81. Okay, if you substitute, you have to get the value. So what will be the value we'll get means it is going to, you check this answer, 1.82 hertz. So for this problem, the solution is 1.82 hertz. So with this, we are coming to this conclusion for problem number 3. Dear students, in this problem, we are going to see with respect to the motor. So the problem is electric motor, which is going to be supported by 6 springs. Okay, this is two-dimensional strain. So we can't able to see that all the 6 springs. Also here, this is the mathematical model of a motor. This is mathematical model of the motor. So the springs are represented. Okay, so we have to take it is going to be 6 springs. So in this case, this is the motor mathematical model and it is supported by the 6 springs. What is this theta? Theta is nothing but the deflection of the motor. So whenever it is going to be deflected, okay, due to because of the disturbance, there is a deflection. So it is rotational displacement. So it is theta. So when I draw the free body diagram for this is rotation. Okay, so x is going to be rotated, then there should be theta is going to be there. That is the rotational movement is there. So how to relate this? So if there is going to be x movement, so there is a angular displacement theta. Okay, so we know that linear displacement is equal to radius into theta. That is the angular displacement. Here, what is the radius? Radius is nothing but the given it is b. Okay, total length is 2b. So here the distance between center to the springs is nothing but b. So x is equal to b theta. Now this problem we are going to solve using the Newton's method. So according to the Newton's method, the applied torque should be equivalent to the restoring torque. So what is applied torque? What is restoring torque? We have to see the applied torque T, a simple formula, that is you very well know that I theta double dot. Once again I am telling that what is theta double dot? It is d square x by dt square. Sorry, it is theta, d square theta by dt square. Okay, so in this case we have to get into the picture of restoring torque. See, listen here. This is the very first problem kind of torque. So, this problem you clearly understood how to derive the restoring torque. Thereafterwards, we will substitute this restoring torque directly. Okay. So, restoring torque we can given it as spring force into displacement. So here, calculating the spring force, there are 6 springs are there, but force we have to get calculate. It is once again stiffness into angular displacement. Already displacement is there. So when I substitute it, restoring torque equal to 6 into stiffness is represented always by K. Angular displacement, we know that it is d theta into displacement B. So now restoring torque equal to, what is our restoring torque? 6K B square theta. Now we have to apply the Newton's principle. This is the applied torque, that is the restoring torque. So when we are applying this, I theta double dot equal to 6K B square theta. So I can write it, since it is equivalent opposite, we have to put minus as per Newton's law. Equivalent, but it is opposite each other. Bring it on one side. So I theta double dot plus 6K B square theta equal to 0. So we can rewrite it as theta double dot plus 6K B square I theta equal to 0. So we come to the conclusion. So you can very well know that x double dot plus omega square x equal to 0 means this way you relate it. Okay, what is this? Both is omega square equal to 6K B square divided by I. So what is this? Then omega, I am writing it here. So natural frequency for this problem is omega equal to root of 6KB square divided by I. Very important problem. Dear students, please listen carefully. Each and every problem, it is a recorded video. Please go through it repeatedly, understood the problem. We will move on to the last problem in this discussion. Listen students, here in this problem, we are going to determine the natural frequency for the system shown in this figure. So here we are having a mass which is tied by a rope around a pulley, and this pulley system is going to be supported in the opposite side by a means of a stiffness spring. Okay, this is once again a mathematical model. Here there may be elasticity that is represented in the form of the K. So it is a mathematical model of a pulley system. It is not directly the actual application. Okay, let me solve this problem in terms of once again the total energy of the system itself. So I am writing it as total energy of the system is nothing but kinetic energy. So you see that there is mass here and also mass here. Okay, kinetic energy of the mass m plus kinetic energy of the pulley. What is the mass here? It is capital M plus potential energy of spring, because that is only the restoring one. Potential energy is there in the spring. Other two, the masses are moving in the form of kinetic energy. Let me have the equation for each and everything. So what is the kinetic energy of the mass? Simple. You already know that it is half mv square, is it not? Once again, I am writing it here. Velocity is represented as x dot. It is equal to dx by dt. Acceleration is represented as x double dot. It is d square x by dt square. Is it or not? Okay. Now let me move on that. Even it is theta dot means it is d theta by dt square. You know very well. Okay, it is we discussed in the last slide. Once again, I am right given it here. So move on to this kinetic energy formula. It is half mv square. Okay, this and all we you know that very well. So let me put in the equation kinetic energy of the mass m. For this mass, it is half m. Since it is b square, is it not? It is velocity. We are represented as x dot square For this, it is half. This is rotational. You see, it is rotational. Since it is rotational, we have to write in the form of I, inertia into theta. It is once again velocity, that is angular velocity square of mv square. Okay, what is this? It is the potential energy of the spring. It is given as half k x square. So we can write all the things put together, that is half m. That is, here you see that you can substitute the previous case we told no x equal to r theta, so that you can substitute here. So it is half m r square theta dot square, okay, plus half I theta dot square plus half k r square theta square equal to, according to the energy, it is going to be total energy in the system should be constant. Okay, so you see that always x equal to r theta. So now we move on. So I writing the equation once again properly. Okay, off all the off. Let me cancel this all the off here itself. Okay, now let move on. So it is mr square k theta dot square. Okay, mr square theta dot square plus I theta dot square plus, then it is going to be k r square theta square equal to constant. Okay, let me differentiate with respect to time. Okay, if I am differentiating with respect to time, m r square 2 theta dot. Okay, if the velocity is differentiated, you will get acceleration theta double dot plus I 2 theta dot, once again theta double dot plus k r square 2 theta. Theta is differentiated the same as theta dot equal to constant is differentiated 0. So now we can cancel this 2 everywhere. What is the remaining things? It is m r square theta double dot, okay, plus it is going to be I theta double dot, then it is going to be k r square theta equal to 0. You can know that also this velocity is there, it is also get cancelled. So from this equation we are move on to this equation. Okay, now we have to rewrite it, okay, in the form of our general harmonic equation. If I'm see that I am combining these terms mr square plus I, that is theta double dot, okay, plus kr square theta equal to 0. So we know that, okay, theta double dot, just simplifying this, k by mr square by I, okay, into theta equal to 0. So from this, it is very well know that, what is very well known? It is omega n square equal to k divided by mr square. So it is k divided by mr square plus I, where I is moment of inertia, is it not? The formula for this I is half m r square. You have to substitute it there. Okay, with this, we come to the final problem solution, that is omega n square equal to, okay, k divided by mr square plus I. This is very important. We have to substitute the moment of inertia. If it is given in the problem, masses are radius and all, then you can calculate the natural frequency of the system. I think you understood very well. Let I stop it here. The next session, we are moving on to little more difficult problems. Another 5 problems, we will see it in this determination of natural frequency for the single degree of freedom systems. Thank you. Once again, we will see with the next session. Thank you, one and all.